Hello and welcome to a new episode on Hyperbolic Orbits. Today, our guest is a highly respected space scientist, especially known for his research in the solar physics community, making his contributions literally stellar. We have with us today Dr. Dibyendu Nandi, who is a professor of physics, IISER Kolkata, where he established the Center of Excellence in Space Sciences India. He specializes in understanding the dynamic activity of the sun and its influence on the near-Earth space environment. Professor Nandi obtained his PhD from the Indian Institute of Science and subsequently spent several years in the US, where he was associated with Montana State University and the Harvard Smithsonian Center for Astrophysics, working on several NASA projects. Since his return to India, he has been pioneering space weather assessment and prediction models for the protection of space-reliant technologies and strategic services. Professor Nandi has received several honors for his research, including the Martin Forster Gold Medal of the Indian Institute of Science, the Harvey Prize of the American Astronomical Society, the Young Career Award of the Asia Pacific Solar Physics Meeting Society, and the Mudali Award of the Astronomical Society of India. Currently, he is a co-investigator of the Solar Ultraviolet Imaging Telescope on board India's Aditya L1 space mission, co-lead of the Education Cluster of the International Space Weather Action Teams of the International Committee of Space Research, and president of Commission E4 of the International Astronomical Union. Thank you so much, Professor Nandi, for joining us today.
Thank you, Sumana, and thank you for inviting me to be part of this podcast.
Thank you. It's such an honor, and I'd love to hear from you about your research. So if you could please share your journey and teach us something about heliophysics today.
Sure. So what I have is I've prepared some slides to talk about the domain of research that I'm involved in over the past couple of decades. And then we can have a discussion on what are the opportunities in space science in various parts of the country and the journey of a space scientist in general, I mean, how it should be, or how, I mean, at least I can tell it from my perspective. Of course, everybody has their own different paths, but we can have a discussion about it. So I'm looking forward to talking to you. All right, let me just share my slides. So I am a professor of physics at the Department of Physical Sciences at the Indian Institute of Science, Education and Research. I have established a center for space science here. It's called the Center of Excellence in Space Sciences India. That was back in 2013, which I led for a while. And now we have my colleague who's leading it. So I came back to India in 2009, and I have focused my research to understand our space environment and its influence on our technologies that we deploy up in space. So my journey started really trying to figure out the sun from a very fundamental level. I didn't really sort of plan out everything that I am today when I started off in my research career and my studies. And as we go along, you will see a glimpse of some of the stuff that excites me. Let me first put my research in context. So we are part of this solar system, which is a region in space which is dominated by the activity of the sun. So we have multiple planets. These planets orbit around the sun, being gravitationally bound to the sun. And the sun is the primary influencer of the space that we call the solar system. And the dynamic activity of the sun extends across the solar system to the edges of this sort of a sphere. Is called a sphere, but it's not really a sphere. It's more of a teardrop shaped structure called the heliosphere. It's a Latin word. Helios means the sun. So the sphere of influence of the sun is the heliosphere. It's interesting that humans have made an object. It's a flying object in space right now, the Voyager 1 mission. This Voyager 1 mission is the furthest that any satellite has ever been away from Earth. Voyager 1 has in fact exited the boundary of the heliosphere and is in the interstellar medium. And this mission carries images of planet Earth, human voices, our songs, creations, songs, and music that has been composed by various composers. It has the sounds of waves, the winds. The idea is that if any extraterrestrial civilization comes across this satellite, they'll get a sense of what is it that exists within the solar system. So the Earth is the third planet after Mercury and Venus in the solar system. And it's important to note that the Earth is the only planet in the whole wide cosmos for which we have evidence of life. We have been searching for evidence of life in other planetary systems. We are now looking at exoplanets beyond the solar system, but we haven't yet found any evidence of life. But we know that life exists on Earth. And I think from that perspective, it is fundamentally important to understand the interplay between planet Earth, our space environment, and the star that hosts us, which is the sun. Because it is this interplay and interaction between the star and our home planet that makes life possible. And I will demonstrate through our work that it is indeed an astrophysical system that we share with the whole cosmos. And our star really governs various aspects of our life. This is a movie that has been made from multiple observations from the Ooty Radio Telescope in Ooty. I really like this movie because this is not a cartoon, it is not a simulation, it's a real observation of plasma density fluctuations within the inner solar system, from the sun, which is at the center, to the outer orbit of planet Earth. It goes on beyond planet Earth, and you see the orbit of Earth and the planet Earth put here by hand. It's just going to tell you the relative location of Earth with respect to the sun, um, in the context of this measurements of plasma density fluctuations. What this is telling you is that the environment that we have always thought, at least in school textbooks, that is completely empty and nothing really goes on in outer space, is somewhat wrong. Of course, there are much fewer particles and atoms in outer space than there is in the Earth's atmosphere. You're talking of a few particles per cc. Sometimes they escalate when there are plasma storms from the sun. But nonetheless, there are extremely energetic photons. There are extremely energetic particles, which have sometimes energies of 1/10 of that of speeds of 1/10 the speed of light, and magnetized plasma, which is coming in from the sun and encompassing the interplanetary space. So we really are actually living in some sort of a changing dynamic environment, and this environment is termed as space weather. And this space weather is becoming more and more important because now we have multiple technologies that drives modern society that is deployed in space, which is satellite based or reliant on satellites, such as telecommunication, GPS navigational networks, imaging, geospatial imaging for even floods, storms. Many of the critical technologies that we take for granted when you use a cell phone, for example, are all channeled through satellites and through space. And so it's important to understand this changing and variable conditions in space that is governed by the sun to understand and assess its impact on our space technologies. So I've spent the last couple of decades in understanding space weather, the origin of it, and trying to predict it, and also at a more fundamental level, trying to figure out what is it that makes life possible on planet Earth, but not on some other planets. So if you had to go back in time, let's go back about 4 centuries to the early days of the 1600s, at the height of the scientific revolution. In about 1609, a revolutionary invention was made, and that was the invention of the telescope. Now, once you have the telescope in hand, humans could train it on the cosmos and observe things that are closer to it with those early ancient telescopes. And some of the early pioneers in this, as you may have heard about, are Galileo Galilei, Johannes Fabricius, Christoph Scheiner, uh, Tycho Brahe, and many other people who followed, including Kepler, who laid down the laws of planetary motion, which then led Newton to formulate his laws of gravity. Um, so in the early 1600s, Galileo and his contemporaries trained their telescopes on the sun, and they discovered that the sun has spots. These are dark spots on the sun, and if you keep counting them, you find that the number varies. And there is typically a cycle. The number of spots on the sun goes up and down with a rough periodicity approximately of 11 years. And this is known as the solar cycle or the sunspot cycle. So what you're looking at on the left-hand side y-axis is the number of spots observed on the sun since the early 1600s to almost the present period. And you find that there is this variation sometimes between 1645 and 1715 AD. There were no sunspots, very few. That's known as the Monroe minimum. That, in fact, coincided with what is known as the Little Ice Age, a time of global cooling on Earth. And then the sunspot cycle activity increased, and then it waxes and wanes every 11 years. So interestingly, what we're looking at is the longest time series of any naturally observed phenomena in the universe. So I'll repeat that again, is the longest time series of any naturally observed phenomena in the universe. This record goes beyond the global temperature record, direct sunspot observations. So this series that you're looking at becomes more interesting when we come to the present. In the early 1900s, it was discovered that the spots, the so-called sunspots, are strongly magnetized. What you're looking at is a magnetograph image made from an instrument that is known as the magnetograph, which uses the idea of Zeeman splitting to map the magnetic fields on the sun's surface. And this is on board the Solar Dynamics Observatory of NASA, the helioscopic magnetic imagery instrument. This dark and white patches that you see on the sun are basically positively magnetized spots of either positive polarity, which is the white patches, or negative polarity, which is the darker patches. So these spots were discovered to have magnetic fields which can exceed a few thousand Gauss, which is much, much stronger than the Earth's magnetic field. And then with these modern satellites, we can also image the radiation that comes from the sun. And this image that you see now is an extreme ultraviolet image of the sun taken from the same satellite at the same point in time when the previous image was taken. And if I keep going back and forth between these two images, you will note something that is intriguing. The sun in this extreme ultraviolet wavelengths is brightest on the regions which are just overlying the sunspots, which tells you that these magnetized spots are actually controlling the extreme ultraviolet radiation from the sun. And this is indeed true for also the X-ray radiation from the sun. You can have an X-ray image of the sun's outer atmosphere, the corona, and we'll find that the corona is brightest over this collection of sunspots, which are known as active regions. Now I can observe the sun for a long period of time. On the left-hand side, you see the sun being observed by the Solar and Heliospheric Observatory, which is a European Space Agency mission. And you see the sun rotating. The sun actually rotates with a period of approximately 27 days at the equator. The sunspots around the sun also rotate with the sun while the sun is rotating. And you see the bright patches are also actually rotating with the sun. They're tied to the sunspots. So that gives you an idea that the sunspots govern the solar radiation. And indeed, if I do this analysis at a much more quantitative level, where I plot the number of sunspots versus time, from 1978 onwards, we have observations of the total solar irradiance. So I plotted the sunspot numbers here on the bottom curve in red, and the blue curve here on top is the total solar irradiance over the same period for which direct observations from satellites exist. So what you see here is that the total solar irradiance, that is the total solar radiation integrated across all wavelengths, that is coming from the sun and reaching the Earth's outer atmosphere per unit area per unit time, is tightly coupled to the sunspot cycle. As the sunspot cycle waxes and wanes, so does the total solar radiation. So the sun's magnetic output, which is the sunspots, actually controls the sun's radiation output as well. And as you know, the sun's radiation controls the Earth's upper atmospheric dynamics. In fact, it controls the dynamics of any atmosphere that any planets have in the solar system. It governs climate in the sense that it's the primary source, the primary natural source of energy input in driving all climate systems. And it's let me just get this call. Um, it's a variable, it's not a constant. What this tells you is that this natural energy input that is coming in into the Earth system is changing in time, and therefore one needs to account for it in models of climate change. Um, this solar radiation also governs the state of the upper atmosphere of the Earth. When the sun's activity is stronger, like at the peak of the sunspot cycle, for example, here or here, the solar irradiance is also stronger. This hits up the Earth's upper atmosphere, which then expands into the low Earth orbit and the also MEO. And what it does there is that it increases the drag on satellites. So therefore, in the calculation of satellite drag, um, you have to account for the sun's radiation level. And the satellite drag results in deorbiting. So it controls the lifetime of a satellite. So when you plan a mission and you have to figure out what is the lifetime of a mission going to be, you need to be worried about the sun's activity, and you need to have this forecast for solar activity in place so that you can make these advanced assessments. When you look at the sun's outer atmosphere, that's the corona. That's the region which is very dynamic. There, the magnetic fields are constantly twisting, churning, um, almost like dancing, destroying each other through a process called magnetic reconnection. And often, when this process occurs, it's a very energetic process. It can result in solar storms, which are known as flares or coronal mass ejections. Here, what you have is a magnetic flux tube on the sun becoming unstable and erupting out in the form of a coronal mass ejection. Coronal mass ejections are the most violent explosions in the solar system. Uh, any one of these events has the equivalent energy of something like a few hundred million nuclear explosions occurring at the same time. I've just put the Earth there for context. The rest of it is actually an observation. So it's a real observation. You see a storm coming out of the sun. The Earth is not there. I put it there just to indicate the relative size of Earth compared to this whole dynamics that is going on. So these flares and coronal mass ejections are not necessarily always impacting Earth, but sometimes they can be Earth directed and impact Earth. When they do, they create what is known as a geomagnetic storm. A geomagnetic storm is a manifestation of the impact of solar magnetized plasma that is essentially coming from the sun in the form of a coronal mass ejection or the solar wind impacting the Earth's atmosphere and the magnetospheric system. This results in the induction of large-scale currents in the upper atmosphere, in the heating of the upper atmosphere, in energizing the atoms of the Earth's upper atmosphere, in ionizing the atoms in the Earth's upper atmosphere, and therefore it gives rise to a whole slew of effects. The geomagnetic storm that you see here on the left-hand side, it's a simulation from the NOAA, National Oceanic and Atmospheric Administration Space Weather Prediction Center. On the right, you see a geomagnetic storm, which is ongoing over the polar regions of Earth as viewed from an astronaut on the International Space Station. Of course, this also manifests down on Earth as beautiful phenomena which are known as auroras. You don't see these auroras from low latitude countries like India. Only only sometimes do you see them when there's a very extreme or violent geomagnetic storm. For example, last year, a storm was induced red auroras over Ladakh. But this is imaged from Alaska, this particular aurora that you are seeing here. And this is a direct manifestation of the solar plasma winds and magnetized plasma from coronal mass ejections interacting with the Earth's upper atmosphere, energizing the atoms. And when they come back to ground state, they emit a photon corresponding to this transition. And then the light, the color of this auroras come from the energy equivalent of this transitions. It's a beautiful phenomenon. If you've seen it, I've seen it thrice in Finland. Well, they have much more devastating effects. For example, geomagnetic storms, solar flares, and coronal mass ejections give rise to this whole cascading space weather impacts, which can result in satellite anomalies. This can result in sensor malfunction in aircrafts flying at high altitude. It can result in communication blackouts, which again, a lot of agencies, including civilian spacecraft, civilian aircrafts, depend on. So, for example, over the polar routes, where the impact of geomagnetic storms are much more intense, these polar route flights are affected by space weather, and often when there is a space weather forecast of a severe storm, planes will avoid the polar routes. Solar flares can also, in high latitude countries, induce geomagnetically induced currents, which can trip electric power grids and also disrupt oil pipelines, sometimes resulting in fires in oil pipelines. They have other effects. For example, very recently, you would have heard about Airbus grounding almost their whole fleet of A320 um, uh, aircrafts across the globe, purportedly due to solar radiation induced impacts on software and hardware. So if you look at the number of satellites that are looking at the sun and space weather from various agencies, NASA, of course, leads the pack, followed by the European Space Agency, Chinese Space Agency, JAXA. There are now more than 36 satellites which are looking at the Sun-Earth system and are studying space weather. India's very own satellite, the Aditya L1 satellite, to look at the sun, is India's first space-based solar observatory, was launched in 2023. And this is a great observatory in the sense that this has multiple instruments looking at various facets of the sun, with instruments that can image the sun's surface. It can look at solar X-ray radiation. And also it is looking at space environmental conditions in situ. In situ implies in the location of the satellite, that is at Lagrange point L1, which is about 1,000,000 kilometers from Earth and along the Sun-Earth line. And when the Earth moves around the sun, this Lagrange point L1 is coupled to this Sun-Earth gravity, so that it also moves along, so that you always have a continuous view of the sun, but you are also close to the Earth, so that telemetry can be facilitated. It's a perfect spot. Lagrange point L1 is a perfect spot for great solar observatories. So let me now, with that motivation, come and give you a highlight, give you some highlights of some of the work that our group, that I have been doing and leading at Center of Excellence in Space Sciences India at IISER Kolkata. Okay, the first thing that we look at is the genesis of solar activity, the origin of the sun's dynamic activity, by performing what is known as magnetohydrodynamic simulations. So these simulations solve a set of equations with appropriate boundary conditions in the sun's interior, and looks at how the sun creates its magnetic fields. And what you see here is a simulation from one of our papers that is looking at the production of the strong toroidal component of the magnetic field that is manifested here on the right-hand meridional cut, which eventually rises up to the surface and produces sunspots. On the left-hand side here, you have the poloidal component, which produces the large-scale sort of dipolar field of the sun. So through these simulations, we can also advance this this modeling techniques by data assimilation to forecast solar activity. And we did this in 2018. This model run used two different models of the sun's magnetic field, one for magnetic field generation in the solar interior, the other for the evolution of sunspots on the solar surface, and we coupled it together, the two models, and he assimilated data from observations, and he drove this model to make the first century scale simulation of the sunspot cycle. And our simulation result, which is in the red curve shows the variation in the sunspot number with time, matched the sunspot observations fairly well. In the background, the black line curve is the observed sunspot time series. So you can see that our simulation did a reasonably good job of simulating the sun's activity the last 100-year time scale. And the simulations are immensely difficult and challenging because you're looking at a star which is far away. You don't have that many observatories or instruments to look at what's going on in the sun's interior. So there is a lot of assumptions that goes on. There are a lot of complexities you have to figure out. And we try to make them as realistic as possible by constraining them with observations. The important aspect of this simulation is we use this after we were confident about reproducing the past activity cycles. We use this in 2018 around this time, the vertical dashed line, to simulate the future activity. This sunspot cycle 25, which is the current sunspot cycle, which you see here, was a forecast. This was a forecast that we issued back in 2018. The red curve is our standard forecast. The two black curves that you see here was the minimum range and the maximum range of that forecast. So back in 2018, we predicted that sunspot cycle 25 will peak in 2024. The peak activity will be in 2024, and that it will be stronger than the previous cycle. Now, if you look at the solar activity of the past few decades before then, you see that it was continuously decreasing. Sunspot cycle 22 was strong, then 23 was smaller, 24 was smaller, and then 25 we predicted to be stronger. This flew against most of the current consensus understanding at that point in time. In fact, the early forecast by NASA NOAA panel, which is the international panel tasked to kind of do this kind of forecast, predicted a weak sunspot cycle 25, and they said it's going to be similar or weaker to 24. But our prediction was that it's going to be similar or stronger than 24. And in fact, we actually were correct. Not only did sunspot cycle 25, now that we have the observations, turned out to be stronger than the previous sunspot cycle. It peaked in 2024 December, which was around the time we predicted it to peak. And this was coming from India, from a small group of scientists working here. This work, the first author was my student Prantika Bhomik, who is now a student in IISER Science, a faculty in IISER Science. This work was quite revolutionary at that point in time, but we're quite happy that that we got it right. We also look at the interaction of the magnetized plasma wind from the sun with planet Earth. So what you see here is a simulation here. Planet Earth is right there in the, right there where my cursor is. And this white lines that surround planet Earth is the Earth's magnetospheric magnetic field. You don't see the magnetic fields, but they're there. Because if you have a compass, the compass will point in the direction of the magnetic fields. Birds use it to navigate. Sailors once upon a time used compass to navigate. We even use it even today. Now, of course, there is global positioning systems. But these invisible magnetic fields are there. And they play a fundamentally important role in the sustenance of life that most of us do not appreciate. What this simulation is doing is simulating the impact of magnetized supersonic solar winds that's coming from the left-hand side, impacting the Earth's magnetosphere. What's going on here is this. So when the magnetized plasma winds from the sun impacts the Earth's magnetosphere, it squeezes the Earth's magnetic field lines into a region which is known as a bow shock in this particular region here, where the density of plasma, that's the magnetic field strengths increase. And by virtue of this increase in the density and of plasma and the magnetic field strength, the pressure that is enhanced in that region is enough to stop the magnetized plasma winds from the sun into entering close to the Earth's atmosphere. So you can think of this as an invisible umbrella, magnetic umbrella, which is due to the Earth's magnetosphere, that is shielding the Earth's atmosphere. And now I put in the Earth's atmosphere here by hand, just to kind of give you this understanding. That blue thing there is a cartoon of the Earth's atmosphere. Remember, it's very thin, only 60 kilometers. Whereas this bow shock that you see here is much further away, at about 6-7 times the Earth's radius in the sunward side. And so the bow shock that is there and the magnetosphere is protecting the Earth's atmosphere from being exposed to the solar plasma winds or solar storms. So at ground level, the atmospheric level, the storms don't come in. This is fundamentally important because if it were to come in, then it will basically couple with the Earth's atmosphere by viscous coupling, like friction, and blow away the Earth's atmosphere. So a simple example I can give is, you just take off some dust in your hand or some powder in your hand, and you just blow on it. The powder or dust will blow away, right? So it's dynamically coupling to the wind that you're imposing through this blowing air, through friction, and that blows the dust and the particles away from your hand, right? Similarly, if the Earth's magnetic field was not there to protect us, the Earth's atmosphere would have been blown away because of the continuous onslaught of the solar plasma wind. The red planet Mars offers a counterpoint. So Mars had a magnetic field earlier because it had a dynamo, just like Earth has a dynamo, which produces magnetic fields in its interior. But at about 1.5 billion years of age of the solar system and of Mars, the dynamo died due to various reasons, and then Mars lost its global magnetosphere. And now its atmosphere got exposed after it lost its magnetosphere to the solar wind. And this is another simulation we have done with a Martian-like planet without a magnetosphere. With the onslaught of the solar wind, there is still the bow shock, but in this case, the atmosphere is not protected. And you see this density here, this density, enhanced density here, that's basically mass loss, atmospheric mass loss. So the atmosphere of Mars is being lost along this long tail because of this coupling with the solar wind, which is flowing from left to right and literally getting blown away by the solar wind. So the lesson that we have here from these two very distinct planets through our theoretical simulations is that magnetic fields of planets are very, very important for the protection of its atmosphere, and thereby allows planets to sustain life. So Mars, for example, has a very thin atmosphere now, which is rich in carbon dioxide, roughly about 100 meters in thickness, very, very small. Compared to 60 kilometers of the Earth, Mars has only a 100-meter atmosphere. Most of it has been lost due to this process. And at least the surface of Mars now is considered not suitable for life. And you have the whole story laid out in front of you of why that is the case. I'll now talk about one technological impact of geomagnetic storms induced by this massive storms for the sun, which are known as coronal mass ejections. So in 2022, February, SpaceX lost 40 Starlink satellites to a geomagnetic storm. There was the forecast available that there's going to be some moderate geomagnetic storms, not very strong storms, but not moderate geomagnetic storms because of the impact of CMEs. But SpaceX went ahead with the launch and launched these Starlink satellites into very low Earth orbit, roughly about, I think, 200 kilometers to do some health checks. That's the typical strategy. And then the satellites that pass the health check are then boosted up to higher altitudes. Well, the satellites, the Starlink satellites, as soon as they're deployed, they got hit by the storm, which in fact was already ongoing when the satellites were being deployed. And they very quickly, over the span of next few days, lost orbit. And there was a catastrophic deorbiting of 40 satellites. And you see in this picture some of the satellites re-entering the Earth's atmosphere and burning out almost like a meteor shower. If you have looked at a meteor shower, it looks somewhat like this, right? So people are wondering what happened because the storms were not very strong. And we put together a team. I led a team of folks from students from the Center of Excellence in Space Sciences here at IISER Kolkata, scientists from NASA and Predictive Sciences Inca, and we all got together to do, I think, one of the most thorough accident investigation that has been done till date on this loss of the Starlink satellites. The paper was published last year. So what we did was we simulated the geomagnetic storm that's induced around the Earth because of the impact of the CME. What you see here is the Earth's magnetic field lines from our simulations. This intense yellow color regions, yellow and greenish blue color regions, are the simulated current density enhancements. So essentially, think of it as regions which are hosting strong currents in the Earth's um, magnetosphere ionosphere system because of the impact of the storm. And on this, we have kind of superposed this sort of imagined orbit of the Starlink satellites. They're not really there in the simulations, but just to kind of give you a sense of what's going on in terms of the geometry that these simulations correspond to. So from this current density enhancements, we could figure out what would be the atmospheric heating that would result from this enhancements in current density. That's because the currents are dissipated because of the resistance in the Earth's upper atmosphere. Now, we did the simulations. On the left here, what you see is the in situ data. The in situ means the in situ properties of the magnetic storms that were fed into our models. On the right-hand side, you see the time series of the simulated current density enhancements. The dashed line that you see here is when the Starlink satellites were kind of launched. And you see that it was all launched when the current density was already enhanced, and then it also again underwent further enhancements due to further hits by coronal mass ejections. In the middle panel here on the right hand side, you see the atmospheric density enhancements. The density of the atmosphere got enhanced because the current is being dissipated uh, and results in heating of the Earth's upper atmosphere. When the upper atmosphere, when you heat a gas, it expands. And so the upper atmosphere expanded into the low Earth orbit. And so when it expands into low Earth orbit, the density of the low Earth orbit also increases. And now the satellites face much more density when they're moving through their orbits, and that creates more friction or drag. You can imagine this, like if you're walking through air just normally, you are sort of fine. But get into a swimming pool and try to walk fast, and you will see what I mean. The density of water is much higher than air, and therefore you are facing a much more stronger drag as you are trying to move through a stronger density medium. So when the LEO orbits have an enhancement in density, the frictional drag on the satellite increases, and the satellite starts losing energy, and its orbit starts decaying. And on the bottom panel, you see the simulated orbital decay rate of the Starlink satellites because of this impact of the storm, the current density enhancement, the density enhancement, and the increased drag related effects cascading one after other. And this also coincided with, or rather, sort of got together, conspired together with some geometric properties of the Starlink satellites, its ballistic coefficient, which makes it somewhat more susceptible to drag. Because the mass is small, the area is larger in the direction of motion. And that all sort of conspired together to bring down the satellites in a catastrophic manner. So this is what was the conclusion, that if you have very low Earth orbit insertion along with moderate geomagnetic storms and not a very helpful ballistic coefficient, which compromises your lifetime at low Earth orbit, then you essentially are doomed. And that was the conclusion of our investigation into this Starlink event. We also do space weather forecasting. This is what I do um, as a passion. Began as a passion. Now it's become sort of a technological enterprise. We're the only group in India which does this. We are one of 3-4 groups in the world that does it systematically and does it well. I think our solar flare forecasting algorithm is one of the best in the world. Our CME arrival time forecasting has been doing as good as anybody else's, and our geomagnetic storm prediction is fairly novel. And I think we are basically right on top of the world as of now in forecasting long-term solar activity, which is the solar magnetic cycle, a decade into the future. So I think, I mean, back in India, we've managed to do all of this, working with students, postdocs, scientists, and often also in collaboration with with the people both in India as well as abroad. It's just given me immense satisfaction of having achieved all of these tasks over the last 2 decades or so. When I think back, this is um, even more sort of satisfying in the sense that when I wrote my PhD thesis, I did, believe it or not, I did not have the term space weather in my thesis because space weather was not so important at that point in time in India. Not many people are working in space weather, either in India or around the world. But in the last couple of decades, it has basically exploded. And I have also contributed to the growth of the field in a fundamental way, and also in a way that can be used to applications for protection of technologies that depend on technologies, satellites that are dependent on space weather. So with that, I will just conclude the research part of the talk, which is to um, um, reiterate that our sun is not just sitting there and not just giving us light, and that's it. It's a dynamic star. It's varying all the time. It creates a variable space environment because of changing particle fluxes, magnetic fluxes, extreme radiation in ultraviolet and X-rays, and also sometimes spews out this very energetic storms called flares and coronal mass ejections, all of which come together to define space weather. And space weather impacts many planetary technologies that we are used to, the satellite operations, aircrafts, radar systems, GPS navigational networks, and a whole slew of other activities depend on this critical technologies that are essentially space reliant. And therefore, it's important to understand the activity of the sun and also simultaneously apply this knowledge to figure out how is this impact, how is it impacting the modern technologies that drives our society today. At a more fundamental and intellectual level, I also work on understanding the possibility of life in other planets and exoplanets. I just got to give you a glimpse of Mars, but I also work on other exoplanetary systems, primarily looking at what can we take away from our understanding of the solar system, because the solar system is a very unique system, the only system that we know has life. And how do we apply this knowledge to other exoplanetary systems far beyond our own to figure out if there is a possibility of life in a planet or exoplanet which is orbiting another star? So with that, I will end, and I sort of will give a break a little bit and ask if Simona has any questions. And then I'll go to the next bit of my talk, which is to look at various programs in space sciences in the country that a student or somebody can be attached to take advantage of. And I'll also give an example of my own life in terms of how my journey was in space sciences, how I became a space scientist, to give you a sense of, well, um, I don't know. I mean, for you to figure out, but the journeys are not always linear. But you can always go through turbulence and various paths before you settle down to something that you would like to do. Subhana, do you have any questions you'd like to ask me at this point in time?
Yes, I do. But first of all, thank you so much. This was a wonderful presentation. My question is that when you do such pioneering simulations, for example, when you do prediction models and you have very less data to validate your current model with, so what kind of approach do you take to
Yeah.
validate simulations?
So that's an excellent question. In fact, so for example, when you think of climate models, climate modelers also use this technique where when there's a lot of uncertainty, and climate modelers are making projections for much longer term, like sometimes 50 years, 100 years, and then you're really dealing with a very highly turbulent, chaotic system, nonlinear as well. So there are a lot of uncertainties, and many of the parameters are not necessarily very well constrained, and these are getting into your models. So when this is not very well constrained, then what you do is you assume a reasonable range of fluctuation that is possible based on your understanding of the system, and you build in those possible range of fluctuations as inputs in the simulations. And then what you create is a whole zoo of simulations, and that's called an ensemble simulation. So you make ensemble runs. So you make multiple different simulations with slightly different parameters. Um, and sometimes the parameters can be different, not slightly, but by large amount if your uncertainty is itself large. And then what you're doing is you are creating, instead of one prediction, you are creating a range of prediction in which you can, from that range, statistically, you can pick up the most likely forecast, and then also the minimum of the range and the maximum of the range. So for example, here, what you have done here is we did the simulation, started the simulation in 2016. We didn't quite know how the ending of the cycle is going to look like. So we assumed multiple different scenarios for the ending of the cycle. And this, you see a little bit of this greenish region, a range here. So that was like the lower range and the upper range of the ensemble. We did about 130, I think, 130 or 134 ensemble runs, varying different properties of the sunspots and assuming different profiles of emergence during this declining phase of sunspot cycle 24, because we didn't know that, know what it's going to be like. And we fed that into our model to predict the next cycle. And then we got the upper range, the lower range, and then the mean, sort of the most likely prediction. So that's how we sort of circumvent this uncertainties that we have in the parameters of systems which are not well constrained. And in fact, I would say the climate modelers have a bit, the weather modelers, climate modelers have it a bit easier because there's now multiple observatories recording temperature, pressure, wind, which are fitting it into your models. Locally, they're well constrained. Whereas for the sun, it's a faraway object, and we don't really have anything that is looking at the interior of the sun in great detail to give us very good constraints. So we have to work with these uncertainties, and we live with these uncertainties and have to be somewhat intelligent in trying to figure out how to deal with them. That's the best we can do. And it seems like we've not done so badly this time.
Definitely not. Thank you. Thanks for explaining that so wonderfully. Now, if we could hear more about how you became a space scientist and how others now can aspire to become space scientists.
So let me first actually come to, and this is not a very exhaustive list. So I would like anybody who is working in any institute that is not featuring here, but is involved in space science, to excuse me if I have forgotten you or your own institute. I'm after a human being. I don't remember everything. It's just a highlight of some of the institutes where you can get involved in doing studies in space sciences. So the Tata Institute of Fundamental Research in Mumbai, which offers PhD programs in astronomy, astrophysics. They also have instrumentation teams which are looking at building, developing space science instruments. The same goes for physical research laboratory, where also you can actually do a PhD. You can also get involved in building space science instruments as well as work in theory and modeling. Indian Institute of Astrophysics is another institute in Bangalore, where you can get involved in a PhD in astronomy, astrophysics, and space science. Interestingly, and this is for those who have a BTech background, the Indian Institute of Astrophysics also runs a MTech program in collaboration with Calcutta University. The MTech program in Indian Institute of Astrophysics specifically targets students with a BTech background. So people who are with the BTech and are desirous of getting the technology knowledge and translating this to creation of scientific instrumentation are sort of preferred for this MTech program of the Indian Institute of Astrophysics. The Raman Research Institute also has PhD programs in astronomy and space sciences. There is the Inter-University Center for Astronomy and Astrophysics, which also hosts PhD programs. The Indian Institute of Science has a PhD program in astrophysics. They're not so much into astronomy instrumentation or space sciences yet, but they also have an undergraduate program, a BS degree program in physics. If you are doing the BS degree program in physics, then from there you can branch into a master's or MTech or a PhD that focuses more on the area of space science. IISc also has various engineering departments, and the Department of Aerospace Engineering is something that somebody who's generally interested in dynamics, spaceflight dynamics, or aerospace engineering can consider for a PhD or MTech program, say. Um, then there is the Indian Institute of Space Science and Technology in Thiruvananthapuram. They offer BTech degrees, they offer MTech degrees, PhD degrees. Also, they offer master's degrees in the basic sciences, as well as various aspects of technical education. So this is also a sought after place for those aspiring to get into a space technology or space science track pretty early on, because if you are doing their BTech program, then you have an opportunity to be directly absorbed into ISRO if you meet certain criteria, and you can qualify through a certain interview. So that's in Thiruvananthapuram. Then there are many IITs now. I've just listed some of them because I am particularly aware of these IITs who have faculty working in various domains of astronomy and astrophysics. IIT Indore has a very nice space science department that they've started, Department of Astronomy, Astrophysics, and Space Engineering. IIT Kanpur has recently started a space science department. IIT Roorkee has recently started a space science center. IIT Bombay has the physics department, which has astronomers, astrophysicists, also instrumentation people building space science missions. IIT Madras has the physics department, which has astrophysicists working in LIGO, gravitational wave detection. They also have, of course, all the IITs have various technology departments where you can get a BTech degree or MTech degree, and then move from there to apply that knowledge into aerospace engineering or the space sciences, which is something that the IITs were envisaged to do. Unfortunately, many students from IITs now just get into more like in software or management kind of work, which I think is a real pity, because uh, the IITs were really meant to produce the technology folks to take India forward in the domains of instrumentation, which I think in India we still are behind the very developed nations. We also have the Calcutta University Institute of Radio Physics and Electronics, who have been historically one of the good groups working at the interface of the Earth's upper atmosphere, ionosphere, and space. Um, they have BTech degrees, MTech degrees. They also have PhD degrees. There could be other universities also in other parts of the country, which I know, for example, the National Atmospheric Research Laboratory, which is part of ISRO, also works with local universities in Tamil Nadu region to host PhD students. Amongst the IISERs, we have IISER Mohali, IISER Pune, which have astronomers and astrophysicists, and of course IISER Kolkata, where we have a few faculty working on various aspects of astrophysics, starting from solar physics to star planet interactions to exoplanetary sciences, which I do, to cosmologists, and then to people who are working in gravitational wave detection, and thinking of missions in gravitational waves, including ground-based and space-based missions. We are the Center of Excellence in Space Sciences India, of course, where you can do a master's thesis, MS by research program, where the coursework load is low, but we expect a strong research orientation in that MS by research program. And we encourage BTech students to come in for that program. So that the idea is that we can then channelize some of the expertise that BTech students bring in to creation of space science models or space science instrumentation. So computational space sciences, computational astrophysics, and space science instrumentation in India uh, do not have enough human resource to sustain the rapid growth in space science that is envisaged to make India a spacefaring power. For that, we need to have many more people doing computation in astrophysics, computation in space sciences, as well as instrumentation in space sciences. And this is some of the things that we are focusing on to try and change and positively impact the current state of affairs. All right. Finally, um, I don't necessarily like to preach because I think that what has gone right for me may not be right for you, and vice versa, right? I do not believe that there is one very well set pathway for everybody, and that you know who you are going to be pretty early on. I certainly did not. Okay, so my path was fairly meandering. I did my schooling in various places, in a semi-rural place in Balasore in Odisha. Then I moved to Calcutta with my parents. I did my schooling here. I went to St. Xavier's College to do my bachelor's in physics. Before that, I did a month of chemistry coursework in Presidency College because at 11, 12, I used to like chemistry and physics. I couldn't make up my mind between the two, and I got into Presidency for chemistry. And then a lot of people in my family and others said, "Oh, chemistry Presidency is great, so go to chemistry." So I got into Presidency. 1 month, I decided that no, this is not my calling. Uh, Not because chemistry is not a good subject. It's because I felt that I am not necessarily able to sort of uh, get happiness out of it. So I moved to St. Xavier's College with to the physics bachelor's program because I did not get into presidency physics. I went to St. Xavier's College to do my bachelor's in physics. I did that, and then I got into the University of Science Integrated PhD program in physics, which was the top priority of students to do a physics PhD in the country at the point in time. So I think I was lucky to have got in. I got into IISc. I was still not sure what I'm going to do. I just knew that I'm going to do physics, but what branch of physics I did not do. I did a couple of summer projects with various people. I talked to various professors. I did some courses, and eventually, I think towards the end of this Indicate PhD program was a mix of master's coursework and then a master's project, and then you sort of get to do your PhD if you qualify the coursework and the project. So the end of the coursework, I decided amongst various things, the thing that appeals to me most was the large-scale universe and astrophysics. And I had a particular fascination for electromagnetism and plasma physics. And so I chose to work with a professor who was working in applications of magnetohydrodynamics and plasma physics to understand the sun. And that is how my journey in solar physics began, which I think was not something that it's not like many people say that, oh, I was born and I went to school and uh, I thought I'm going to be an astrophysicist, or I looked at the stars and I knew when I looked at the stars I'm going to be a space scientist. Nothing like that. I'm night blind. I can't see the stars very well, except when I simulate them. So yeah, so it was for me. I think it was that kind of a journey where often I did not know. I went through uncertainties, and then things fell in place, and I took decisions based on what felt to be the right thing to do at that point in time. Um, but a couple of things I learned along the way, and that is what I want to say, because I think those are common to being a successful scientist. And I don't really know whether this just applies to science. I think it applies everywhere. But I think the science is you have to be curious about the world around you. I think a general curiosity about the world around you, not curious because your parents say that you have to study, or that somebody says that, oh, you have to get that degree, because once you get that degree, then you are done. That makes you, then the degree becomes more important than the subject or the topic, and then it's a bit hollow. You don't really develop this wonder about the world around you. I think you should be generally interested in the world around you, interested in figuring out things as you move along, right from scratch, at the foundational level. So you should really invest in skilling from when, if you want to be a scientist and a space scientist, the most important things are understanding of physics, understanding of mathematics, uh, uh, differential equations, understanding of data, how to handle data, being interested in data around you. And a lot of data is now publicly available for you to play with and plot with and make sense of, and tinkering with things if you want to be an instrumentation person. I think this is one thing, but there is no shortcut. There is no shortcut to hard work. Okay, nothing. I mean, you hear about the people are genius, people are born genius, they can dream up things. I think everybody was working hard. Okay, I mean, even Einstein was slogging. So I think hard work is essential as well. And I think there is this, this you have to accept in your mind, that if you have to be successful in anything, you have to be able to work hard. Um, Now, do you want to be a scientist, like get a PhD and work in trying to figuring out like really fundamental things, unknown things at a very intellectual level, or do you want to be a technology enabler? Now, if you want to be a technology enabler, you can. Scientist is like you go down the typical academic track, your bachelor's, master's, PhD. For a technology enabler, you can get a BTech or you can get an MTech. Or if you really, when if you really are creative, you don't even need a degree. You can create a startup company where you employ people like us and other people with a BTech degree out of IITs, right? I mean, look at people like Elon Musk, Jeff Bezos, who's the Microsoft founder? I'm forgetting his name. Uh, uh,
Bill Gates.
Bill Gates. Many college dropouts, right? I mean, hello, they're employing people who are, who went through the PhD and masters and BTechs in colleges like Stanford, MIT, IISc, IIT Kharagpur. I mean, uh, you can just be a creative person who wants to and enable others and achieve uh, the creation of something, a product or a mission. And for that, you just need to be adventurous. I think being adventurous is also very important. You don't necessarily need to have gone down this track where you can write down beside your name, I have a BSc, I have a MSc, I have a PhD, hey, I'm a doctor, I'm a professor. I think those are all eventually meaningless. What is eventually meaningful is, are you creating? Are you doing it? Are you doing something different that is enabling the world in a broad sense, or are you even making a difference locally to your domain? And I think that anybody can do that. And I think what's important is for you to also have a positive frame of mind to be able to do this. I think is very, very important, because I see this particularly in the new generation. I have nothing against them, because I think that I mean, many of us, I think we constantly interact with newer generations, and we really value that. We value that because it keeps us mentally young. We are challenged on every day to deal with somebody who are younger and younger than us as we grow older and older. It might, nobody talks about it. It might feel easy, but it is not. Okay, because you're dealing with people with different backgrounds, different mindsets, different expectations, right? Um, what we see sometimes today is that people get very easily isolated, and they get into programs where they've been forced into doing something, and their life is a mess. Okay, we see people who are not able to take the stress of the coursework, the stress of the research that is involved. And I'm not going to make it easy. It is stressful. Okay, I mean, when we went through it, it was also stressful. Anybody who says that it is going to be easy, or it's just, it's a charm, not true. Not true. Okay, I mean, I'm trying to fool you if I say that, right? If I get a student and I tell them, I'm going to make your life easier, you get a PhD in 5 years, I'm lying to them. And not only that, I'm destroying their career, because I might make it easy for them, but after 5 years, reality will hit them and they'll realize that they've been fooled. So I think it's important right at the beginning to appreciate what you're getting into. And most of this is also going to be quite stressful, right? Academia is stressful. There is no hiding away from it. But there are ways to deal with that stress. And I think often people forget that. And I think it's important that you worry about your mind, because that is like the sun controls everything in the solar system. The mind controls everything that you do. You could be a genius, but your mind is not in it. If your mind is off, you've not nurtured your mind, you can go completely haywire. The things that we should, happiness is to be cultivated. I think it is important. Take time out, right? I mean, work hard, play hard, right? Play harder if required. I think that is something that is fundamentally important. I personally hold. Okay. I am part of many adventures. I still nurture happiness. I try to get out as often as I can. I tell my students to also do that. Yeah, I am demanding of the work that they have. They should do. They should. They should meet up to certain expectations. But beyond that, what they do is something that is up to them, right? Uh, it's important to cultivate friendships beyond work. You have to have multiple pillars. I think those are important. I'm talking from an academic viewpoint now, because I'm assuming that people who are listening are going to listen to this podcast are going to come into academia, right? And come into this pot boiler of a situation where you have ambitious, very bright people trying to top everything out, ace everything out. And I was not necessarily like that. Okay. And you will find yourself in this milieu, right? And if you are not nurturing your mind, you can lose it completely, right? This is a situation that happens far too often in academia. More so in academia, because people at a very young stage, whose minds are not necessarily matured enough, because none of our minds were mature enough at that point in time, right? Coming in from the confines of a protective household where nobody questions you. Your parents are your best friends. I think, right? They don't question anything, right? You have not been, in that sense, you have lived a protected life, and then you come somewhere where you are constantly being challenged. You are being constantly asked to meet up to certain expectations, right? In this environment, you have to meet up those expectations if you want to go up the system. But there are also certain things that you can do to make sure that your mind is healthy, and that mind is ready to accept all these challenges and deal with them, right? You don't need to top, right? But you need to survive and move on to the next level where you can do something out of your life. That is important, right? Not everybody can be a topper. I think this whole system is a mess, a little bit of a mess, where we just value the topper, right? Uh, but I think if you're curious, if you're hardworking, if you nurture your mind to be creative, and you look around yourself and see what is the difference I can make do in this world, either in my immediate domain, a local domain, or across the world, you will be able to make a difference, right? How much is a relative thing, and that is something that is for others to judge. But what is the most important thing is what makes you happy, because I think that is fundamentally more important. So I think with that I will end, and then I will Suman, if you have any questions, I'm happy to answer them.
This has been so wonderful, Professor Nandi. That's the scientific research that you talked about, then about your journey, and you told things that are extremely valuable to students right now. Um, I'll go back to my own self a few years ago, and it's exactly this kind of advice that saved me. I was studying, doing this, stopping everything, and then made a mess out of everything. So one very kind scientist, she took me out of that, and she took me to an observatory. I was at the observatory, and in the middle of the night, she used to take me to the telescope room, and she would teach me how to observe, how they manage the data, how they observe fast stars. And that's how I developed that scientific curiosity, and that eventually brought me out of that stressful mess.
Mm-hmm.
I can't thank you enough for this entire presentation. This has been a wonderful, wonderful session. Thank you so much for taking the time out to do this today.
Thank you. It is a pleasure. I think I'm always up to it, because I think we benefit from students. I think that is fundamentally important to acknowledge, because many of the work that I've talked to you about, it was impossible for me to having done it alone. And so it's important for us to also nurture the students and ensure that the next generations also remain healthy and are able to come up in an environment where they know that there are challenges, right? Are aware of them, but in spite of it, also know how to survive those challenges, deal with them, and still contribute. I think this is something that is a generational thing and has to be handed down from one generation to another. And I'm happy to be part of it. And thank you again for giving me this opportunity and this podium. Thanks.
Thank you. And to everyone watching, I hope you like this episode. Please like, share, and subscribe to this channel because we're going to have some more wonderful episodes soon coming up. And thank you, Professor Nandi. I hope more and more professors like you keep inspiring us and keep nurturing students. Thank you.